Larry Berry Jr. back for some more physics. We're doing some graduate level classical mechanics book reading and starting with the Cayley-Klein quantities, Goldstein 4.5. So we'll get started with that, and I'll probably do various topics throughout the day. We have seen that only 3 independent quantities are needed to specify the orientation of a rigid body. So earlier we saw that we had one for 1 point, let's say x, y, z, and then one here, which would only be in relation to that one. A phi, and then the third point would be only in relation to those two, theta. This way should be all you need. Maybe adding an extra term, but we'll keep going. That's the general idea. Nevertheless, there are occasions when it is desirable to use sets of variables containing more than a minimum number of quantities to describe a rotation, even though they are not suitable as generalized coordinates. Thus, Cayley-Klein introduced a set of 4 parameters bearing his name to facilitate the integration of complicated gyroscopic problems. The early angles are difficult to use in numerical computation because of the large number of trigonometric functions involved, and the 4-parameter representations are much better adapted for use on computers. Although the 4-parameter sets, I wonder if this is, let me make sure this is a section that we need to do. This doesn't seem familiar. The other day that we have a sort of classes covered outline. 4.3 through 4.6. All right. Although the 4-parameter sets are of great theoretical interest in branches of physics beyond the scope of this book, wherever rotations or rotational symmetry are involved. It therefore seems worthwhile to briefly describe these parameters, leaving the details to Appendix A. The 4 Cayley-Klein parameters are complex numbers denoted by, so does this ring a bell? Complex numbers. Alpha, beta, gamma, and delta, with the constraints that and this is an aside, which may be missing a detail on the first one. E equals gamma star and delta equals alpha. Is that a actual asterisk that they're giving information on, or it just means star? This is a short section. In terms of these numbers, the transformation matrix of a rotated body is given by this. Maybe I'll just copy that down. So now we have this transformation matrix. Matrix A is real in spite of its appearance, as we can see by writing alpha equals E naught plus I E3 and beta equals E2 plus I E1. For real quantities, E0, E1, E2, and E3 are often referred to as the Cayley-Klein parameters, but should be called the Euler parameters to be correct. They satisfy the relation the interesting mix is E0 is separate. E1 has an ion beta. E2 is separate on beta. E3 has an ion alpha. A bit of algebraic manipulation then shows that the matrix A can be written in terms of the four real parameters in that form there. Save myself from writing these full matrices. Hopefully I don't have to, I mean, it's such a short section, I don't think I'll need to know this in detail. So this is not something, apparently it's something we should read, but I definitely do not remember going over this in class. So I'll assume familiarity is needed, but not specific understanding. Looks like we're replaced alpha with what it is, beta with what it is. And what I mean, the complex conjugate. So gamma is the complex conjugate of beta, and delta is the complex conjugate of alpha. So that's how they replace gamma and alpha. So basically, if you put a complex conjugate on alpha, you get delta. So delta would be E naught minus I E3, and gamma would be E2 minus I E1. So the complex conjugate, you simply put a negative on the imaginary component of the number. And using this, they replaced everything. Here's the squared on everything. I think it's necessary to do that algebra all the way out. So I can see how it's working. The reality of the matrix elements is now manifest. It can also be easily demonstrated that the matrix A in terms of these parameters cannot be put in the form of an inversion matrix S. An examination of the off-diagonal elements and their transposes shows that they all vanish only if at least three of the parameters are zero. We cannot then choose the remaining non-zero parameters such that all three of the diagonal elements are only one of them are -1. All right, well, I'll go ahead and move on from that. Euler's theorem. All right, so let's go ahead and adjust the scrolling text. Rigid bodies. I'll change that on the screen real fast as well. A semicolon and that those who come in can see the full one. The ring. All right, let's see what we have here. In discussions of the previous section, the discussions of the previous section provide a complete mathematical technique for describing the motions of a rigid body. At any instant, the orientation of the body can be specified by an orthogonal transformation, the elements of which may be expressed in terms of some suitable set of parameters. As time progresses, the orientation will change, and hence the matrix transformation will be a function of time that may be written as A of t. If the body axes are chosen coincident with the space axes at the time t equals 0, then the transformation is initially simply the identity transformation. So A at t equals 0 equals A 0 equals the identity matrix. At any later time A of t, at any later time A of t will in general differ from the identity transformation, but since the physical motion must be continuous, AT must be a continuous function of time. The transformation may thus be said to evolve continuously from the identity transformation. Makes sense? This is rotating smoothly. With this method of describing the motion and using only the mathematical apparatus already introduced, we are now in a position to obtain the important characteristics of rigid body motion. Of basic importance is Euler's theorem. So let's write this down. Let me check something really fast. Back. Euler's theorem. General displacement of a rigid body with one point fixed is a rotation about some axis. Theorem means that for every such rotation, it is always possible to find an axis through the fixed point oriented at a particular polar. The theorem means that for every such rotation, it is always possible to find an axis through the fixed point oriented at a particular polar angle stated in phi, such that a rotation by the particular angle psi about this axis duplicates the general rotation. The theorem means that for every such rotation, it is always possible to find an axis through the fixed point. So you have a rigid body, you have a fixed point, it is always possible to find an axis through the fixed point oriented at particular polar angles, phi and theta, such that the rotation about the particular angle psi about this axis duplicates the general rotation. You put an illustration of this. Such three parameters angles characterize the general rotation. It is also possible to find three Euler angles to produce the same rotation. If the fixed point not necessarily at the center of the mass of the object, an Euler angle, going back to before, is these three angles here. Euler angle is three successful rotations to a new coordinate system. So the first angle is about z, the next angle is about the new x, and the last rotation is about the last z. So we're using the x convention in this book. And this would be the fixed point right here. The fixed point, not necessarily at the center of mass of the object, is taken as the origin of the body's set of axes. Then the displacement of the rigid body involves no translation of the body axis. The only change is in orientation. The theorem then states that the body set of axes at any time t can always be obtained by a single rotation of the initial set of axes, taken as coincident with the space set. In other words, the operation implied in the matrix A describing the physical motion of the rigid body is a rotation. Now, it is characteristic of a rotation that one direction, namely the axis of rotation, is left unaffected by the operation. Thus, any vector lying along the axis of rotation must have the same components in both the initial and final axes. That makes sense. The other necessary condition for a rotation that the magnitude of the vectors be unaffected is automatically provided by the orthogonality condition. Hence, Euler's theorem will be proven if it can be shown that there exists a vector R having the same components in both systems. So R equals A, R equals R, this is the vector along axis of rotation. It doesn't change. Equation 4.48 constitutes a special case of the more general equation. R equals A, R equals lambda R. Lambda is some constant which may be complex. Technically, you could always write it as complex as just sometimes d. So a complex number is a plus ib, and b can be 0. So technically, every number is complex with a 0 for b if it doesn't have an I. The values of gamma for which 4.49 is soluble are known as the characteristic values or eigenvalues. Here we go. Linear algebra. This term is derived from the German eigenwert, literally proper values. Matrix, since equations of the form 4.49 are of general interest and will be used in Chapter 6. We shall examine 4.49 and then specialize the discussion to equation 4.48. The problem of finding vectors that satisfy equation 4.49 is therefore called the eigenvalue problem for the given matrix. And equation 4.49 itself is referred to as the eigenvalue equation. Take a break later, by the way, and do some undergraduate stuff. Correspondingly, the vector solutions are the eigenvectors of A. Euler's theorem can now be restated in the following language. Diagonal matrix specifying the physical motion of a rigid body. Fixed point with one point fixed. Always has an eigenvalue of +1. The real diagonal matrix specifying the physical motion of a rigid body with one point fixed always has the eigenvalue of +1. The eigenvalue equation 4.49 may be written as there will subtract lambda r from the right, so now it's equal to 0. I factored out the r, and I multiplied the lambda by 1. So I is the identity matrix, which is 1 down the diagonals and 0 is everywhere else, so that it takes the same value but just puts it in the form of a matrix. So this was a vector lambda. We turned it into a matrix with the identity matrix, whereas now it's a matrix of the same value. Okay. Now they're going to expand this thing. We have, it's like they're using a 3 matrix. So now we have a lambda 1. Can't use lambda 1, 2, and 3. So lambda is just lambda. I have to keep that in mind. Lambda is not a vector. This is a complex constant. So it's just a number. I was still thinking it was like a vector, like a series of constants. So I'm getting too vector happy. And anybody who pops in, let me know if you have any questions or comments. I'll be happy to answer. I am checking the chat. So we have a minus lambda. So basically, let me draw this out. So we have this. So this is lambda times 1, 1, 1 with a bunch of zeros, everything else. So you get lambda, lambda, lambda with a bunch of zeros everywhere else, which we then put there. So we have a11 minus lambda, a12, a13, a21, a22 minus lambda, a23, a31, a32, a33 minus lambda, x, y, z equals 0, 0, 0. So then looking back at the book, oh, see, they did make a lambda 1 and 2 and 3 later. All right, well, or was I? I'll just wait until they do it actually. 450. So then I'm going to distribute that. So we have a11 minus lambda x plus a12 plus a13 equals 0. A21, well, my x x's, y's, and z's. A11 minus lambda plus A12y plus A13z equals 0. A21 plus A21x plus A22 minus lambda y plus A23z equals 0. And A31x plus A32y plus A33 minus lambda z equals 0. And this becomes 4.51. Equation 4.51. Equations 4.51 comprise a set of three homogeneous simultaneous equations for the components x, y, and z of the eigenvector R. As such, they can never furnish definite values for the three components, but only ratios of components. So this makes more clear uh, the problem in other contexts where like coupled oscillators, which I'll probably do later, where you get the ratio of the vectors to each other, like how much of one vector uh, uh, you know, correlates to how much of the other vector. I may actually do that problem after we finish this section because it's still related. Might take a break and come back and do the coupled oscillator. Physically, this corresponds to the circumstance that only the direction of an eigenvector can be fixed. The magnitude remains undetermined. The product of a constant with an eigenvector is also an eigenvector. In any case, being homogeneous, equations 4.51 have a non-trivial solution only when the determinant of the coefficients vanish. Only when the determinant of the coefficient of the vector equals 0, Product of a constant with an eigenvector is also an eigenvector. In any case, being homogeneous, we can have a non-trivial solution only when the determinant of the coefficients vanish. So this is an eigenvector as well, the same eigenvector. Uh, and the sum of this also, at least the product of this is also an eigenvector. So the lambda that will keep that as an eigenvector non-trivially, being the homogeneous, the determinant has to equal 0. Okay. So now we're starting to catch up with one of the last things we did in class, and this is making sense here. I think I wanted to save a certain file to look at a time like this. I think I saved the wrong file. Did I? Let's see. No, save it now. We can look at this thing together. Mm, this thing in the wrong spot. See? Take a second. So I'm looking at the example we did in class, and this does align. So we'll continue with that. This is looking good. There's some details we didn't get to yet, but I'm sure we shall. Yeah. So I'm seeing where we are, and we're going right along. Right. So only when the solution, I should say, and thanks for popping in. Whoever pops in, let me know if you have any questions, any comments, and you're watching the chat. Non-zero solutions. We'll go ahead and work this out with an example in a moment. We're keeping up nicely. All right, so back to the book. 4.52, which is here. Equation 4.52 is known as the characteristic or secular equation of the matrix, and the values for lambda for which the equation is satisfied are the desired eigenvalues. Euler's theorem reduces to the statement that for the real orthogonal matrices under consideration, the secular equation must have the root lambda equals plus 1. For the real orthogonal matrices under consideration, the secular equation must have the root lambda equals plus 1. So at least one of the lambdas must equal plus 1 because that one axis is not being changed. So the fact that one of the axes is the rotation about is equivalent to this. But this one right here is one of the lambdas where because that lambda is 1, the axis does not change. It's my understanding. And this is rotating about that axis. In general, the secular equation will have 3 roots with 3 corresponding eigenvectors. For convenience, the notation x1, x2, x3 will often be used instead of x, y, z. In such a notation, the components of the eigenvectors must be labeled as x, I, k. The first subscript indicating the particular component, the second denoting which of the 3 eigenvectors is involved. Okay. So we have x k I the e x1. A is lambda I-E lambda 2. The first subscript indicating a particular component, the second denoting which of the 3 eigenvectors are involved. Eigenvectors are involved. Okay, hold up. Maybe I mixed up what they mean by component. Sometimes I hate formal notation, but I'm sure in the end it makes things easier. Talking about the group of equations 4.51. We're going back to here. Actually, J A I J X J K equals lambda K X I K. And let me check the print version momentarily. Summation J A I J X J K equals lambda K X by k. Copy this over. Separate these out. Call this 451 prime. So we have becomes x1, x2, x3, two, x2, x3, x3. So then we have one double prime. Let's see where we're going. So we have this. So we have this. Put here, put this here, put that there. The last one. Now we have it in the form notation there. So now we have the sum of a j and x j k equals lambda k at I. This is I j j I j. Three k k k k k k. This is jk. See the j. Notation is not quite clear to me, but they have a delta there as well. Makes more sense with the oh, yeah. I guess technically right, well, I'll just let that be for now. We do see that, I mean, this form here makes sense when you distribute the x jk's and then bring each one to the other side here to the positive, where we can see how the first row lambda 1 x1, the second row lambda 2 x2, the third row lambda 3 x3, and the matrix is simply the general matrix A multiplied by the vector of the um, in question, x, y, z, x1, x2, x3. Both sides of equation 4.53 didn't have the form of a matrix product element, which, as I was saying before, is the product. The left side is the product of A with the matrix X. Well, even though I think this notation is pretty obtuse, but they are getting the point across, I guess. You have this. The left side is the product of the matrix A with X, having the elements X, J, K. The right side as the product of X for the matrix whose JK's element is delta JK lambda K. So basically we have I that properly. Yeah, that should be right. So this is the matrix lambda, 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 and this is the vector x. So basically we have lambda, lambda, the zeros, x, y, z. That's going to equal x lambda, x1 lambda 1, x2 lambda 2, 3 lambda 3. So that's a different way to look at that operation. The a minus lambda I, which is just what we had before, I suppose. It's just this right here. I mean, it's simple enough. The last matrix is diagonal, and its diagonal elements are the eigenvalues of A. And so therefore designate the matrix by lambda. This is still just lambda multiplied by I. So then we have a r equals lambda. Easy enough. And if it's 4.54, equation 4.53, that implies the matrix equation. Yep. Is equal 4 multiplying from the left. So hold up now. They put the X on the left side. Maybe it's a typo. They do have typos in this book. Uh, so lambda is is uh is the same either way. So a that that inverse equals lambda. Let me down momentarily. The left side is in the form. Now the left side is in the form of a similarity transformation operation on A. We have only to denote x inverse 1 by the symbol y to reduce it to the form of equation 4.41. everything to the other side. You can make a mirror image out of it. Thus, equation 4.55 provides the following alternative approach to the eigenvalue problem. We seek to diagonalize A by a similarity transformation. So we can find the eigenvalues of A by diagonalizing A via similarity transform, which is x inverse A x equals lambda. And this will output the eigenvalues output as diagonal matrix. That's neat. Each column of the matrix used to carry out the similarity transformation consists of the components of an eigenvector. Okay? The elements of the diagonalized form of A are the corresponding eigenvalues. That's pretty neat. Sometimes I hate math. Sometimes I think math is cool. The Euler's theorem can be proven directly by using the orthogonality property of A transpose. Consider the expression A minus identity matrix A transpose equals identity matrix minus A transpose. Makes sense. Just distributing this. If we take the determinant of the matrices forming both sides, we can write the equality that determinant of A minus identity matrix A transpose equals determinant identity matrix minus A transpose. And what this means is the determinant of A minus identity matrix determinant of A equals determinant of identity matrix minus A transpose. So A minus identity matrix, determinant transpose equals identity matrix minus E transpose. And this is 4.56. To describe the motion of a rigid body, the matrix A at time t must correspond to a proper rotation, eigenrotation. Therefore, the determinant of A and of its transpose must be +1. Further, since in general the determinant of the transpose of a matrix is the same as that of the matrix, the transpose signs of equation 4.59 can be removed. This must be a proper rotation for rigid body motion. Thus, determinant of A and determinant of A transpose equals +1. This means that A minus 1, 1 equals A, A minus equals 1 minus A 4.57. Minus 1 equals A. Okay. Equation 4.57 says that the determinant of a peculiar matrix is the same as the determinant of the negative of the matrix. Suppose B is some n by n matrix. Then it is a well-known property of determinants that we have A is defined as n by n. So the determinant of negative B equals -1 to the n of the determinant of B. the determinant of negative b. You multiply b by -1, take the determinant. That's the same thing as the determinant of v multiplied by -1 times the number of rows and columns. So if there's only one row and column, then the negative determinant is negative. If it's 3, negative, 4, positive, and so forth. Since we are working in a three-dimensional space, n equals 3, it is clear that 4.57 can hold for any arbitrary proper rotation only if think about this. Since it's 3D, the negative of the determinant, right? Comparing equation 4.58 with the secular equation 4.52. You can see that one of the eigenvalues satisfying the equation 4.52 must always be lambda equals +1, which is the desired result of Euler's theorem. Thus, at least one equals 1, because one axis is being rotated around. Right. I'll go ahead and pause here, take a break. Been going for just over an hour. I'll probably come back and I'll see how much more of this we get to get to an example. And I'll finish reading 4.6, then we'll do an example. Maybe I'll bring out the undergraduate problem. So look for that later. I'll see you all in a bit.